I see people coming. Everybody. Hi, everybody. I guess we can start. Bruno, where are we?
Let's wait a minute, maybe, but yes, you should be able to start.
Okay, welcome, everybody. My name is Alexandre Castellane. I am with Bruno Mesnet. We both work for IBM, and we are dedicated to CAPI, OpenCAPI team. So we are based in Nice, while our team is based in Montpellier, south part of France. I'm very glad today to speak in the name of our team to present you OpenCAPI OC-Accel, which is a framework, as we'll see in a minute. So the first question we might raise is, why do we need the framework, what it is, where can we find it, how can we use it? So we'll try to answer these questions very briefly. OC-Accel is a framework that uses acceleration based on hardware acceleration using FPGA. We'll see in a minute what an FPGA is. And we use through coherent access that OpenCAPI provides on power systems. What is an FPGA? We'll see how it can complete and not compete with GPU acceleration. Where can we start? We'll see a brief introduction of the GitHub structure and how to use it. And in 3 steps, we'll see how we can simulate and generate a configuration and deploy on Power 9 system. At the end, we'll see if we can use Python or not, and we will have a brief view of a test case. So first, we'll cover OpenCAPI very briefly because Alan Cantel has already made a presentation earlier today. We will go through the FPGA technology. As we said, we'll cover what it brings. We will see in details what OC-Accel can offer to you. And we'll go through a very interesting test case that Philippe will be presenting in this OpenCAPI thread. All right, so first a very brief introduction, speak about OpenCAPI Consortium. Most of you have attended Alan Cantel's presentation or Mendy's presentation. So most of you are aware that there is a site where you can find information. There are many open source information as far as the technology is usable directly, and you can get different levels of hardware. It stands for Current Accelerator Processor Interface. So what you need to have in mind is that the OpenCAPI is a unique technology that offers you to access to the host memory without any buffering. So it's to my knowledge, the only direct and nice access to the host memory. So let's begin with the FPGA technology. We'll go in details what it brings. First, it stands for Field Programmable Gate Array. So think about a huge number of cells, logic cells, that have not been interconnected. So the last layer of a chip design has not been made, and it is left to you as a designer the capability to interconnect these. To achieve that, you will be helped by software, which is dependent on the provider. The main provider we work with is Xilinx, so we use the Xilinx suite to prepare this last layer in order to configure the chip to do whatever we need. The configuration is usually stored in local flash memory on the board that you have bought, usually from a supplier or that you have made yourself. And this flash memory at the power-up will configure the chip and finish the last interconnection to do whatever function you have programmed. Think about a Lego. So we'll see how OC-Accel uses this Lego. I shouldn't say Lego, I should say think about cubes, storable cubes. The FPGA is made of, as we said, a logic that can be reprogrammed. So it's up to you to prepare the programmation. It offers you configurable IOs and high-speed serial links, which we use in the OpenCAPI technology. It has advantages in terms of flexibility. Once you have bought a board containing an FPGA, you can reprogram it for almost forever, maybe not forever, but for thousands of times. It offers you high capability in terms of parallelism. You can create small functions that do a small job, and you can have many of them in parallel. It allows you to have very deep pipelines, so it can be very interesting in terms of, for example, compression or whatever. And you have integrated hard IPs, which simplify a lot the big functions like access to PCI connection, access to Ethernet, or access to memories. So once you have understood that, historically, we have been using FPGAs by programming them into a structured language or languages, which are named Vhdl. The two main known languages are Verilog or Vhdl. Both are a way to describe the logic. So it's not code, it's a way to describe what you want at the end to be interconnected. It used to be require specific skills, and we will see how we can override these constraints that many people still have in mind today. Once you have synthesized software, people would say compile, but it's a synthesis. Think about a compilation. Then you can get a binary file that you store in the flash memory, which allows you to program the board when you begin to power up your circuit. An example of a large card, which comes from Bitware, there are many of them. AlphaData is also a big supplier of cards. This integrates also a zinc circuitry, which hosts Cortex ARM technology. So it's not only an FPGA, but it also hosts a microcontroller that can host codes in turn. Right to the topic, what can OC-Accel do with an FPGA? You can say, okay, how can I be helped to prepare my logic, because it seems very complex to me. So think about these cubes that are unorganized, and we need to prepare some organization which we can duplicate eventually. So this is why I have drawn the beginning of a castle, and you can do according to the size of your FPGA, you can consider multiplying and parallelizing things. So the goal with the system we have in our hands is to be able to ease the preparation of this logic. And functions will be not running like code. They will not be running sequentially, but they will all be running in parallel if it's your desire, because you are in front of logic. So OC-Accel will help you to prepare these castles or these houses, but it will also ease the interconnection of all this logic with your power host system, thanks to the OpenCAPI technology. So it will not be only a fast link, which you can think about at first sight, but it's also a way to exchange data from the FPGA to the host memory, as we'll see. An example to fix ideas for people who are not knowledgeable in FPGAs, an example of integration into a large 9H7 AlphaData card. I forgot to mention the supplier of the card, but it's usually a chip that we use on AlphaData cards. Here we are just considering the chip itself, which is provided by Xilinx. In this 9H7 card, which hosts XU, I don't remember the reference, 27, I think. My colleague Bruno here, he constrained the logic to be into a slice here. So we can see different area. This is the area in yellow that the action, we'll see in a minute what it is. This is what you have described, what you wanted to prepare inside the logic. This is your part, which is yellow. In blue, we see the, remember this interconnection layer that IBM is, or OpenCAPI is taking care for you. So we need to embed some logic here. And then you have the snap core, which is doing some functions to allow you your action to talk to the memory. So coming one step higher, the question can be raised, how can we choose between GPU and eventually an FPGA acceleration? So first of all, they are not competing. They are not on the same topics. they are not doing the job in the same way. So one solution can be better in one domain, the other in another domain, and sometimes we can be very happy to use both of them. So first of all, the GPU is very well known. It's aimed at dealing with compute-intensive applications. It's a bunch of teeny CPUs which are using parallelization to do a huge number of tasks. Where the FPGA is a bunch of logic, as we said, so it's very low latency and it's very predictable. So we can know exactly how many clock ticks. Clock ticks means the clocking system inside the FPGA. We can know exactly how long a function will take to be operating. So it's more real time, and it can be it's not sequential, and it can be using high parallelism. So let's have a word on what we have as advantages. So we know that software is very quick to develop. It can be reused. It can be patched. The disadvantage is that it's very slow to run because most of the time it's a sequential operations that we want to run. Hardware is known to be very fast. It's known to be reduced consumption. It's known to be very low latency because it's aimed at doing the task, so it is really tuned for this task. We can have also parallelism and high bandwidth to access to the memory, as we'll see in an example with OpenCAPI. And we can also dedicate specific areas and optimize the area to do that. The cons of that is that, as we said, we used to have for a long time very heavy source code to define the logic, and this was requiring specific skills, and it was known to be very costly because the maturity of the technology was not developed enough, and the cost was, of course, a little bit higher than it is today. So it was leading to much longer time to market. What if we could remove most of the disadvantages of the software and the hardware sides? So the goal of the combination of FPGA and OpenCAPI and the framework of OC-Accel is to offer you reducing the disadvantage of not using software. So we'll be using software to describe the logic, and this is what makes Xilinx part particularly very interesting. So we will describe the logic using C or C++, and we will use Xilinx HLS tool to convert our description into a digestible, is that English? Something that the FPGA can understand. Why the hardware was very long to develop, now thanks to this HLS and thanks to the OpenCAPI very fast access to the memory and direct access to the memory, we can reduce a lot these disadvantages. So let's go into OC-Accel. Remind me what time we left. We leave the
until 5. Until
okay,
5.
So 12 more
15 minutes.
15 minutes, good. So we'll go where the code is located. So it's an open source development that is following the SNAP, which was concerning CAPI 1 and CAPI 2 technology. As Alan mentioned, it's now for years that this technology is existing. We have taken the time to do the draft, and now it is a third generation, so it's pretty mature and very operational. The code can be found here on GitHub. The documentation can be accessed here on GitHub too. And to set up a project, we'll see how, we'll not see, but it's very easy to reuse CAPI 1 or CAPI 2 development in case you have done it already. And it's very easy to exchange cards using existing cards or preparing a new card that you have in mind. We'll see how we can simulate, generate the binary content, and see an example of our friend and colleague, Philippe, that he has done with OC-Accel. OC-Accel overview. So the goal for you is to take a yellow program that you have that will connect an application, and you know that this application is taking time to do repetitive tasks that you think, and talking with people using FPGA, you have a guess, and you would like to go deeper into subcontracting some of the actions that are in your application that you would like to put into an hardware action. So the goal is to get some of the application and transfer it into the FPGA. On the left, you have your host server, and on the right, you have one card embedded into your server, interconnected with the OpenCAPI technology. Coming with OpenCAPI will come a bunch of hardware description that will go, remember the blue area of the chip, that will allow the intercommunication of the host memory and the FPGA. And on the software side, very teeny and small libraries, because most of the driver has been performed and written in hardware inside the Power 9 chips. So this reduces a lot the software complexity on the software side, which is a very good advantage. On the right-hand side, we see the card is hosting different hardware interconnected parts. There can be a DRAM that can be hosted by the card. There can be cages that allow you to connect to the outside world with Ethernet or anything you could think of. It can be, for example, a converter, like very high-speed converter to link to a 5G system that collects and treats on the card a huge amount of bandwidth and data with your own designed DAC or ADC or DAC configurations that can directly talk to the host memory of the server. So you can embed also 5G type applications. A word on the documentation. A colleague has spent some time to make it, I shouldn't say the adjective that comes to my mind, but nice looking, I should say. And this is written in a server-like system, so you can update, suggest updates or modifications. What we have basically inside the structure of the SNAP or the OC-Accel today is a bunch of examples that you should rely on to develop your own examples. We will go briefly on the image filter and say a word about the example in Python. So in each action directory, you see we are in OC-Accel actions directory. You will find a software subdirectory which hosts the main so-called application that will be launching the hardware, and we have a hardware subdirectory in which we have described in C most of the time, but you can also still describe everything in Vhdl languages, but we prefer using more recent way to describe in C++ the actions. You will see the examples of the description. We will briefly explore a pixel manipulation example that we have taken from our colleagues and friends from HPI, and we will see a Python example that has been developed by our research department. So first thing you need to do is to set up your Xilinx tools. Most of the time, people will use Xilinx parts, so most of the cards, if not all the cards, are hosting Xilinx components, which is the FPGA provider. So you need to set up some things to make sure that you access to your card. I won't go into the details. Then while typing make snap config, which is really the first thing, you want to type, you will get a very simple open source menu that is based on an open source configuration tool that will allow you to avoid main mistakes that we have prevented you to do. So we canalize you to get into basic examples, and we subselect for you the possibilities according to what you have chosen. So here I chose an AlphaData 9v3 card hosting a VU3P Xilinx part, and I selected the image filter. Once I've selected this, the system will set up some environment variables, and these variables will be read, and then I can make a simulation. You see that in less than 5 minutes, I can be ready to make a simulation. Then I can launch on a small image a transformation. The goal is to transform an image into another and see if the result is agreeing to what I expect. Once I have, sometimes I can encounter problems, so I can enter into a debugger, should I do so. And for the first step, I can make sure that every pixel, this is a bitmap example, every pixel is going into the sequence that I've prepared for them for the manipulation. An example of the code. So the manipulation of the pixel is really written in pure C. We see here that we prepare pixels, and if the pixel has not enough red inside its coding, then we will replace each component of the pixel with a gray computed value. Otherwise, we will reproduce the red value, the red containing pixel. So you see, it's pretty easy. The transformation, if the pixel has not enough red, then I replace by a grayscale. Otherwise, I just duplicate the pixel. Then we can deploy on the power system. We need to prepare the image. So we say make image. This can take time. And the binary file, which we hopefully get after some time, can be transferred to a power system. And on the power system, we can simply run, check first that we have a card. After the process of making image, I check that I have an OpenCAPI card. It's present. I check that OpenCAPI contains my code. I didn't go into the details. And then I can run my code and transform the image to get what I expect. Okay, so all pixels containing a big proportion of red is great. And I can check my performance. Here we provide an example of performance. It's an example that Bruno just updated. So we see that to transfer a 256 megabyte file, we transfer that from the host to the FPGA RAM, which is a RAM that is hosted by the FPGA card. We transfer at a speed of almost 18 gigabytes per second, while returning from the FPGA to the host was transferred at the speed of almost 21 gigabytes. And this is the, let's say, slow access to the local RAM, which is not the latest technology on this card, and this is about 12 gigabytes. Make sure that you use the NUMA control to make sure that the FPGA is attached to the core, to the core that is talking to the RAM. A Python example is provided. You need to set up your environment because, as you know, Python is not that easy to manipulate if you have not the right version. Once you have set up your environment, you can follow the guide that we have provided on this example that you will find here. So yes, we can define the application in Python. We will not define the hardware action in Python, but we can exercise an hardware action using Python on the top of it. And hopefully we will speak a word, but please attend the presentation of our partner and friend, Philippe from Paul Scherrer Institute, based in Switzerland. We would really like you to follow this very interesting test case that he has produced, he is using currently or intending to use. In 2018, they had an issue because the latest detector family is providing much larger bandwidth than the previous generation. So they were limited to 4 megapixel transferred at about 1 kilohertz for every image. And this was achieved with a 9 gigabyte per second transfer. Now, using OpenCAPI in few months, not less than few months, but in few months, they were able to program and acquire using the FPGA and using the cages. They were able to acquire the pixels at the speed of 10 megapixels at 2.2 kilohertz. So this is the ultimate goal. But right now, for today, the goal is to multiply by 5. But very quickly, they were able to make a ×2 multiplication of bandwidths. And please attend PSI presentation in this track. I think we say OpenCAPI track. So should you have any questions, I would forward you to one of us, either Bruno or Fabrice or myself, and we'll be very glad to answer your questions. We have, I think, only 1 minute for questions. So please do so. Thank you very much for your attention. So I see many people attending. And for the moment, I don't see any questions. So please feel free to contact us. Bruno, I think we are finishing time.
You can raise your hand if you want to ask a question directly.
And I see Philippe is attending, so Philippe will correct me if I have said something wrong in his presentation, that I would encourage everybody to attend, please. it's very impressive the job he has done with OC-Accel. All right.
I see no question.
There is one question you said, Bruno?
I see no question at this moment.
Okay. Oh, somebody said thank you very much. One question, if we can use OC-Accel with a core. Could you precise the question? Can I allow
Like A2I.
Peter, permettre de parler? Peter, if I did not make a mistake, you are allowed
It's
to
like
speak.
A2I. Can we use OC-Accel with A2I?
Oh, okay.
So today OC-Accel is using OpenCAPI interface. All the internal design is open source. It just, I would say, do a bridge between AXI and OpenCAPI. So as soon as you want to integrate something which can be attached to either of these interface, I guess you can. A2I, there may be some, well, may not be obvious, I think. Today it is, OC-Accel is not designed for it. Okay, so OC-Accel today has been developed as a master. Part of the design has been modified to be also a slave. If you listen to Christian Pinto's presentation later today, you will be able to see how to have a master and a slave. It's not built on OC-Accel, but you could do it in a future release, I will say. So today, OC-Accel is enabled only as a master and not as a slave, but it should, well, it's just a matter of finishing the design. Okay, so feel free to ask any question. You can find, feel free to send them in the Slack. We will try to answer as best as possible.
Do you have the time of Philippe's presentation? It's difficult for me to access my other screen. So we can forward them to...
It is just after this one.
Okay. In the same track.
In 7 minutes.